In this presentation, we're going to discuss UV spectroscopy. I know that I've kind of dissed UV spectroscopy a bit in this course because it isn't the #1 method that we go to determine molecular structure, but it is useful in getting a few simple facts of a molecule out, like the fact that it's conjugated or how conjugation is changing during a reaction. We're not going to spend very much time on UV-vis spectroscopy in class, so I'm making these videos to supplement those brief discussions. So UV spectroscopy, and really UV visible spectroscopy, was probably the first method used by chemists to explore atomic structure and then later molecular structure. This goes way back into the early 1800s. The Germans were making fine optical instruments back then, and of course it was only a matter of time before they started to look at light with those optical instruments, and Joseph Fraunhofer was the #1 optical technician in Germany at the time, and he invented a spectrograph, really. I suppose the first spectrograph. It was a telescope connected to a prism. Then he was able to move it around in precise ways and measure the angles. And as he looked carefully through the colors of the spectrum, and of course Newton had already shown that light could be divided into colors by a prism, but he noticed an absorbance spectrum, the classic Fraunhofer lines. You'll see them right here, the lines of the solar spectrum. And at the time, of course, no one understood the nature of these or why they would happen. That would wait another 100 years till deeper understanding of the electronic structure of atoms came along. But this was the first hint that there was more going on in light than just the fact that it was made up of many colors. Now, Robert Bunsen was a great spectroscopist as well. He's pretty famous for the Bunsen burner, but he only invented the Bunsen burner so that he could fry elements to look at their emission spectra. And what he discovered was that the emission spectra of elements was the same as the absorption spectra that we see in the Fraunhofer lines. This proved that those lines were due to the absorption of elements in the solar atmosphere. So he was basically able to demonstrate that the sun's got more going on in it than just bright light. There's his spectrometer from 1874. It's a collimator that will take the light in from the burning flame where you might have sprinkled some sodium to get the emission lines, and then you go through that series of quartz prisms, and then you're able to use a precision telescope and measure the angle and get the exact they didn't understand wavelengths or frequencies back then, but certainly you could get the exact position of the line. Now, what would you do with that information? Well, another 50 years later, that finally, the information needed to understand the solar spectrum was finally generated. Lots of people were looking into the nature of atoms at that time. Atomic theory was being developed. The fact that there was something going on with atomic bonding was understood. The electron was just around the corner. Well, I guess the electron was understood as coming from atoms at that time, but how did electrons and atoms connect together? Was it the, what do you call it, the raisin muffin model, where electrons are embedded in sort of a big, soft, puffy nucleus, or was it something else? Well, Bohr proposed the famous, his famous model was that the nucleus was a small particle that was orbited by the electron, and that the electrons had very defined orbits. Now, Bohr was a big deal. Of course, he won the Nobel Prize when he was 37. He's on Denmark's money. He's had an element named after him. I mean, you really just don't get bigger than Bohr in physics. Many people consider Bohr to be the mother of quantum mechanics, and we only say that because, of course, Max Planck was the father, so that job's taken. But he was a really important scientist and advanced the theory of atomic structure quite a lot with this idea that you have these energy levels. And of course, we now know them as the quantum energy levels, the principal quantum number of an electron in an atom. And there's level 2. And the Fraunhofer lines are, in fact, the Balmer series for the hydrogen atom is many of the Fraunhofer lines. There's the longest one. There's the next shorter wavelength. There's the next shorter wavelength, from 2 to 3, 2 to 4, 2 to 5. So if these are the energy levels for the electrons around a hydrogen nucleus, we can see the Balmer series right there. And the Balmer series, you recall from physics, is what we see in the visible spectrum. The energy transitions from the very bottom electronic energy level are, we can't see them with our eyes, but you could detect them in a UV spectrometer, of course. So there's the visible spectrum, and we can see 3 of the lines of the Fraunhofer lines are in fact due to hydrogen. And you expect that. The sun's a big ball of hydrogen. But now that we know this, this really helped physicists understand the nature of the sun. I mean, was it just was it oxygen and hydrogen burning? I mean, no one knew really. And as atomic theory became understood, and of course nuclear fusion and the secrets of that are still a few years away, but we're starting to understand that the sun is got a lot of hydrogen in it. But it has other things. It's got sodium, it has oxygen, it has iron. The sun has iron. So there was a lot of information coming out of this, and this was a very important field at the time. Now, we're organic chemists, so we're not really interested in the electronic structure of the elements. We have bigger fish to fry. We want to look at organic molecules. So can we take this technology and can we use it for organic molecules? Well, remember, we're talking about molecules, so we're going beyond atomic orbitals. We need to talk about molecular orbitals. So let's take hydrogen, the simplest sort of molecule we could make. We can take two hydrogen atoms and we can bring them close enough together that their orbitals interact. Now, the math of orbital interaction is such that things will become more and more stable as we overlap those orbitals until internuclear repulsion cancels that out. And so we'll reach an equilibrium where we've got maximum orbital stabilization countered by the nuclear repulsion of positive charges, and that's the bond length. But what do the two orbitals look like when they're combined mathematically at that distance? Well, if we set the two hydrogens one bond length apart, and now we got to do some really complicated math with two atomic orbitals from hydrogen. And so here's the math, all right? Now, first we have to understand the complicated rules of quantum mathematics, and what they really all boil down to is that two circles, when you add them together, make an oval. And what happens if I subtract two circles from each other? So there I've changed the sign of one. I have a one with one sign, one with the opposite sign. So, you know, -1 plus 1 is a subtraction. So let's now subtract them from each other, and they cancel out in the middle. And of course, you'd expect that an anti-bonding orbital doesn't have electron density between the two atoms, and a bonding orbital has maximum electron density between the two atoms. And of course, there's only two electrons, and they're both going to be in this bonding orbital, and positive interactions that give electrons more room to spread around in are lower in energy than negative interactions that restrict the opportunity for electrons to spread out. They're higher in energy. So the bonding orbital is lower in energy. The electrons can find a lower energy situation, and this is why we have covalent bonds, and we're not living in a disconnected world of gas. All right, so what's the energy from this transition here? Is there a UV spectrum that would promote an electron from this sigma orbital to that sigma orbital? And there is, but it's a pretty intense UV spectrum. I would not want to be exposed to a wavelength of 100 nanometers. That would be a pretty intense sunburn really quick. So that's an extreme vacuum UV. It will not penetrate the atmosphere. So fortunately, we don't have to worry about that. We don't even need ozone to block this out. As long as there's oxygen in the air, that will quickly create its own ozone. Now, why do we call these sigma bonds? We recall from organic chemistry or earlier courses that sigma refers to the symmetry of the bond. If I look along the bond axis, whether I'm looking along the antibonding or bonding orbital, I see a circle. A circle has infinite symmetry. All sigma means is circular symmetry. A sigma bond is a bond that has circular symmetry in its electron density along the axis. That's all it means. All right, so hydrogen's not really an organic molecule. Let's look at methane. We call methane the smallest organic molecule, if you want to do that. We have the hydrogen atomic orbitals, and here we have 4 carbon sp3 hybrid atomic orbitals. And all sp3 hybridization means, as you recall from your chemistry courses, is that I have taken the 3p orbitals and the 1s orbital around that carbon. They're still there, but I have just recalculated them and imagined orbitals that line up with the 4 carbon-hydrogen bonds, or that are all 109 degrees from each other. I have just created orbitals mathematically that fit the tetrahedral geometry that we know this molecule will form. Now, I could do that math from scratch. I could just take the hydrogen atoms and place them in a tetrahedral arrangement and then calculate their individual interactions with each of the 3p orbitals and the central s orbital, and I'll get exactly the same answer. I'm just doing this in advance. It's just graphically simpler. So if I take this sp3 orbital that was combined, remember I used bits of all 3p orbitals and the s orbital. That's why it's sp3. I had to use them all. Let's add them together. So I'm going to have positive interactions which are stabilizing and negative interactions which are destabilizing. I take the 2 orbitals along each bond So there's a set of these for each of the 4 bonds. And if I add a kind of a circle to a circle, I get a kind of an oval. We didn't change the lobe off of here because, of course, the math was all focused over on this side. So you can see how the shape of this sp3 hydrogen bond, carbon-hydrogen bond, is pretty similar to the sp3 orbital itself with added electron density from the hydrogen. Subtraction works out just like you'd expect with a node down the middle. So circle plus circle equals oval, circle minus circle equals, they cancel out in the middle. And of course, you can expect that where we have more room to spread out electrons, lower energy, constricted situation, higher energy. There's 8 electrons to parcel out, and they're all going to end up in the lower orbitals. Now, this is a vast oversimplification. These 4 sp3 orbitals are not at 90 degrees to each other, so they'll further combine into more classical molecular orbitals that you'll get if you do calculations. But we can always imagine them as local molecular orbitals. All 4 are identical local molecular orbitals. So let's just keep it at that level for now. Now, the energy difference between a carbon and a hydrogen sigma bond to its antibonding orbital is a little less than with hydrogen. You can see that the absorbance goes a little higher in the vacuum UV, and that's because carbon and hydrogen are not identical molecules, so you don't get like absolutely perfect overlap. So that's an alkane UV spectrum. Still way down in the vacuum UV. Now, I can guarantee you we do not have an instrument that can look at 150 nanometers. I have a pretty good UV. It's super excellent, but it will not look down at 150 nanometers. So, and really it's pointless to even try because the atmosphere in your instrument is going to absorb light at that wavelength. So everything's going to look dark. So that is the sigma orbitals of methane. Let's look at something where we have a chance of seeing it in UV spectra with our instruments, and that's ethylene. Ethylene has a double bond, so let's examine its molecular orbitals. Now, of course, if I've got this double bond, we know we're dealing with sp2 hybridized situations there, and all that means is I know that everything's planar in ethylene. I already know that. One of the p orbitals in each carbon atom is going to be sticking out of the plane, and it won't be involved in the sigma bonds. So there's a spare p orbital. I only used 2 of the p orbitals to create the sigma bonding network. So sp2, the s, and 2 of the p orbitals. There's a spare p orbital on each carbon. There they are. There's the 2 spare p orbitals on each carbon that won't be used. So let's make the sigma bonding network. I've added my circles together, and I got ovals. I subtracted them and got canceling out in the middle. That's the carbon-carbon bond made from 2 carbon sp2 orbitals. There's the carbon-hydrogen bond made from 4 carbon sp2 orbitals and the 4 hydrogens. And they'll of course be arranged along the axes of their various as they fit in the structure. But notice what I didn't use. I did not use these 2 p orbitals. I've used up all of these orbitals. I have not used these 2 p orbitals. They're still there. They'll of course are standing right next to each other in 2 adjacent carbon atoms. So they'll combine. And what happens if I add 2 p orbitals together? Using these strict mathematical rules of quantum mechanics, 2 circles make an oval. So the 2 circles above make an oval, the 2 circles below make an oval. There is your classic double bond, your pi bond. And the subtraction is exactly what we expect. We'll cancel out in the middle. And we have 2 electrons to go in there, and there is our double bond. This is the highest occupied molecular orbital, and it defines nucleophilic attack by the double bond onto an electrophile. You'll tend to attack out of the middle of that double bond because that's where the electron density is. Nucleophilic attack onto that double bond, if it occurred, would occur at one carbon or the other because that is where the empty spaces are, isn't it? They're not dead center, nothing dead center. If I want to get orbital overlap as I approach a nucleophile's orbital to this antibonding orbital to add into that double bond, I'm going to add into one side or the other side. So molecular orbitals define the chemistry of a molecule. Here we're looking at the energy difference between here and here. That looks a lot less than the energy difference from here to here. So I bet pi to pi antibonding, pi to pi star, is going to be a lot lower in energy. Look, much longer wavelength. And my spectrometer could actually see most of this peak. So we are now into the range where we can actually start observing. UV spectroscopy is going to require that there be these lower energy transitions to be useful. We need double bonds at the very least. So that's an alkene. So we can see alkenes, we can see things that have these lower energy transitions. Now, I kept calling these pi bonds, and again, that just refers to the symmetry. Why do we call it pi? Because if I look along the bond, I see twofold symmetry. Pi just means twofold symmetry. I could flip that over and it would look the same shape. Ignore the colors, they're about the sign of the wave number. The shape represents the electron density, and that's what we're talking about. Here the electron density is in a circle when I look down the bond. Here it is in a dumbbell, twofold symmetry. So if we see twofold symmetry, that's a pi bond. That's really all it means. Now if I conjugate a double bond, you can imagine that I'm spreading out the electronic system, and of course if things are spread out, they're lower energy. Basically I'll now have 4 pi orbitals instead of 2. That means that they're going to be spaced closer together, and look, we're starting to move higher up into more convenient areas of the UV spectrum to look at. I'm not going to need the cleanest, most special quartz cuvettes anymore. I can just use the regular cuvettes that don't clean so much. Now, so conjugation helps. Let's examine the molecular orbitals of conjugation. Butadiene, classic conjugated molecule here. 2 double bonds. I'm going to model it as the 2 pi systems. I'm just going to do the pi system, and I'm going to model the 2 pi systems as if I started off with a pair of double bonds that are conjugated to each other. You could, of course, do this from scratch with 4 p orbitals as well. But let's just imagine that I'm starting off with a pair of pi bonds, and they're both the same energy. And of course, if they combine, they're going to positively, negatively, and you can imagine that we can do the same thing with the antibonding orbitals, combine them positively and negatively. What would the new 4 molecular orbitals look like? Because I started with 4 orbitals here. I started with 1, 2, 3, 4 p orbitals. I've got to have 4 molecular orbitals in the end. Or you could also say I started with 1, 2, 3, 4 pi orbitals. I've got to have 4 in the end. What will they look like? Well, if I add 2 ovals together, what do you get? A bigger oval. Watch this. Quantum math in action. If I subtract 2 ovals from each other, what do you think will happen? Well, they'll just cancel out. So you can see if I add those together, we have a node between them. And now let's look at an interaction between these antibonding orbitals that maximizes as much positive interaction as possible. So if I basically arrange the signs so that we have positive interaction in the middle, we can add it up to this. And if I arrange the signs so that we have maximum destructive interaction, we'll get that. So that is quantum math. Oval plus oval equals bigger oval. There's the bonding orbital. We'll put the electrons in. You'll notice how electron density crosses the entire system here. This is why this bond here doesn't rotate freely. It can rotate, but it does not rotate freely. It takes some energy to do so. And then there's the highest occupied molecular orbital, defines how the chemistry operates. The chemistry, things that are electrophiles will add to this double bond or that double bond. And that's because that's where the electron density is. So transition from this pi orbital to the next pi orbital here is going to be a little lower in energy than if we were going from just the original pi orbital to the original pi star. So you can see, look, that energy is less than what we started with. So conjugating gets you more orbitals. The more orbitals you get, the closer the HOMO and the LUMO get to each other. So the pi to pi star energy requires less and less, or the pi to pi star transition requires less and less energy and easier to do. So a conjugated diene is going to have absorb at a longer wavelength, or less energy is going to be required. Now, we've been talking about double bonds, and we're going to talk about other double bond compounds as we go through this presentation. So now would be a great time to open up your organic chemistry book and review nomenclature of ketones, esters, nitriles, imines, all those molecules that we'll be talking about all through spectroscopy. You don't want to forget your organic chemistry, because this is an organic chemistry course. So, now, a lot of transitions that we see in UV spectroscopy are a lot higher than 250 nanometers, and these tend to be even weaker, even lower energy transitions, but they're not between 2 pi orbitals. If you go from 1 pi orbital to another pi orbital, you're following the same symmetry. It's easy to do. The electron doesn't have to change basically the kind of orbital it's in. But if we went from, say, a lone pair, sp2 orbital like lone pair, to a p orbital, the symmetry is slightly the same, but not exactly the same. We have what's called an n to pi star transition, or a non-bonding orbital to a pi star orbital. So here I'm looking at the higher part of the spectrum, like there's 150, here's 150. So we're looking at these two right here, and I've placed them here. There's our pentene, there's our conjugated pentadiene. And if I was to look at So those are easy, and look at the absorption coefficients. 18,000, really high absorption coefficient here. Here it's 40,000. That's a logarithmic scale here. Every one of these notches is tenfold greater absorbance. Look at the absorbance spectrum for aldehyde. A lot higher, but that is not a transition from the pi to pi star orbitals of that double bond. It's a transition from a lone pair here into an orbital, into the empty pi star orbital of that double bond. And it's much weaker. Look at that. The extinction coefficient is just above 10. That's like, it's 1,000 times weaker in absorbance than the double bond, but it's still it's going to be easily detectable by our UV instruments. And this is usually what you're looking at. You're looking at the UV spectrum of DNA, things like that occur around 250, 260, 270. It's these N to pi star transitions that you're really looking at. And then of course there's that shoulder. When you get a little lower there around 230, it just rockets straight up toward the ceiling. That's of course where you're starting to get the double bonds in. So this is sort of a very useful place to look for structural information about your electronic system. So big difference in absorption. Now let's talk about sort of the electronic details of this. Now, because we're changing symmetry, it is a forbidden transition. But rules, no, more like guidelines, really. Forbidden doesn't mean forbidden. Forbidden just means really unlikely. So here's an easy to do, very likely transition. Here's a tough to do, very unlikely transition. Have you ever, you ever like tried to throw a tennis ball through a chain link fence? I guess that can't be done. Try and throw a golf ball through a chain link fence. Usually it'll just bounce off, but you can occasionally get it through, as opposed to throwing it at just a giant hole. So if it's less likely, it's just more difficult. So here's our starting orbitals for a carbon-oxygen. This is formaldehyde, keeping it simple. I've got the carbon-hydrogen s orbital here. So they're just going to build all the orbitals that we're building this out of. The oxygen atom is going to be sp hybridized in this model, just for the calculations. There's the two p orbitals of the oxygen we're not using. Here's all the sp2 orbitals of the carbon. One pointing this way, one pointing this way, one pointing this way. Hydrogen is a bunch of s orbitals, and of course there's a spare p orbital on the carbon there. And I'm going to take this basis set of orbitals and combine them. You can imagine that the first thing we're going to do is we're going to make the carbon-oxygen sigma bond. So there's the carbon-oxygen sigma bond, and there's its anti-bonding orbital, and the carbon-hydrogen sigma bonds. They're here and here. So once we fill those with electrons, they're going to be way down there. We're never going to really observe those in the UV spectra. What's more interesting is the pi to pi star orbitals for the carbon-oxygen double bond. And you can see, of course, the more electronegative nature of the oxygen causes there to be more of the oxygen p orbital in the bonding orbital and more of the carbon p orbital in the anti-bonding orbital. And you recall that from your organic chemistry courses and how you might construct molecular orbitals. But look at this. Coming over is a spare unused oxygen sp orbital. We didn't use that. We used the sp orbital pointing toward the carbon here, but that one never got used. It's non-bonding. And look, a spare p orbital from the carbon. And those are the non-bonding orbitals. And when we fill everything with electrons, what's our highest occupied molecular orbitals? It's this pair of non-bonding orbitals that never really changed or did anything. Now you might say, why didn't I sp2 hybridize that oxygen in my mind? I could have, and I would have had a pair of sp2 orbitals here, but that wouldn't be exactly correct because you'll notice how these are at 90 degrees to each other and not talking, and the actual molecular orbital calculations with the computer reveal the orbitals to have this structure. But they do, in total, the electron density of these pairs sort of combine to create a nice electron cloud around that oxygen, a nice even electron cloud. So on a macroscopic level, it'll behave the same, whether you imagined it as two sp2 orbitals or this pair. But there's our non-bonding, highest occupied non-bonding orbital, and there's the N non-bonding to pi star transition. It's a lot less than the pi to pi star transition. So it's a lot lower in energy or higher in wavelength. It's also less likely, so a much lower absorptivity. Now, it's forbidden, so it's going to be weak. And if we conjugate, look over here on the right, if we conjugate, we're going to, again, spread the electrons out and move that up. So If we look at sort of the change in UV spectra, we can see changes in conjugation. We can estimate the conjugation by the frequency. There's tables of data that you can use to calculate what the frequency would be with a simple carbonyl, and then how it would change if you add, as you add double bonds at other groups. And so you can kind of come up with an estimate for the level of conjugation from UV spectroscopy. So it's somewhat useful for that. All right. So let's talk about kind of practical uses of this. So if you're an astronomer and you're looking at a star and maybe a planet passes in front of the star, you know what you're looking for? You're looking for the absorbance spectrum of the light from that star. Maybe you can spot chlorophyll. Well, here we're just looking at the star, and we can see the Fraunhofer line, so we know that the star has hydrogen, and you can get all the other elements in the star. It looks like it's got not too much sodium in this star. And so these are all nice sharp peaks because, of course, this is a gas and it's all atoms, separated atoms of hydrogen. So, of course, being a gas, it means the atoms aren't really talking to each other. They're just floating around. They're not in a liquid. They're not rubbing up against each other. They occasionally crash into each other. For the most part, they're traveling alone in space. So that keeps things simple. But we don't have that. We have broad, look at these broad peaks here. Broad peak, especially here, like really broad peaks. Why are our peaks, when we look at them in sort of more concentrated systems, why do we have these like broad peaks? And that's because, of course, things are more complicated than just simple, completely separated atoms floating around in a very high vacuum. This has to do with the many other quantum levels that are involved. So we've only been talking about electron levels, but in a molecule, there is more than its electron energy. There's a whole bunch of bonds. And those bonds vibrate. And that's vibration. There's many vibrational energy levels, so there's many places to land. Once we get jacked up in energy by UV absorption, we don't have to just land back at the vibrational energy we started at. We could land at another vibrational energy level. And this spreads out the possible absorption energies. So let's look at that carbonyl peak there in the aldehyde. There's our various non-bonding to pi star interaction there. So that's where we're starting, and that's where we're ending up. And when we look at that transition, one thing you'll notice is if I looked at that with a microscope, there's the energy level for the electron. But of course, that bond is also described by a series of vibrations. So there's the vibrational energy levels for this bond. It matters more here where the actual bonding electrons are. But if I eject these from this orbital and they land in this orbital, they could land at any of these vibrational energy levels. So we could go from the first electronic level and the first vibrational energy level to their corresponding energy levels, or we could go to the second vibrational energy level, or we could be going from the first electronic energy and the second vibrational energy down to the first vibrational energy level of the next one up, or up to the third. So you can see that we're starting to spread the possibilities here and make for a peak that doesn't just have one frequency, but is a sort of a range of frequencies on either side of the central frequency. And each of these vibrational energy levels, there's the electronic energy, there's the vibrational energy, there's the next vibrational energy. Within each of those are layered on top the rotational energies of the whole molecule itself. So you can land on any of these. So when we do these transitions, we're going to transition upwards a whole electronic energy level, but where exactly do we land? Above and below that, there's a spread. So that's why we end up with these broader arrangements and broader absorption frequencies. Now, of course, remember that we've got a condensed material here. Maybe it's a liquid that we're looking at. It's certainly often in solution when we do UV spectroscopy. That means we've got hydrogen bonding interactions with maybe the water solvent, or polar interactions with the polar solvent, whether it's ethyl acetate or chloroform, or van der Waals interactions. The molecules are bumping into each other. Molecular orbitals are coming. They're not coming close enough to overlap because of electronic repulsion, but close enough to change their energy levels slightly as they interact. And so you have this whole schmear of the fact that we're dealing with a million possible microenvironments in any solution. And UV spectroscopy is an instantaneous method. It sees all of these simultaneously, and basically we're going to end up with these nice broad peaks. So what have we talked about as we've introduced UV spectroscopy? I'd like to say that it is useful for looking at electronic energy transitions. How useful are these for giving us some structural information? Well, the pi to pi star transitions really are useless. So using UV spectroscopy to look for the structure of sigma bonds, not too practical. If we're using enough energy To observe that, we are probably annihilating the molecule, because if you promote the energy in a sigma bond to its antibonding orbital, you have effectively broken that bond. Pi to pi star transitions are more practical, and we see those, and especially in really highly conjugated systems, those can become very useful as the absorbance moves well up into the UV and the visible. Perhaps what is more useful is when you've got molecules that have polar atoms in them as part of a conjugated network, we can get these N to pi star transitions if there's lone pairs around, and as a result, this comes well up into the visible and the UV, and this is an area that's very easy and convenient to analyze, and conjugation is going to affect the spectrum there. And so what can we get from UV spectroscopy, UV visible spectroscopy? Usually fairly decent information about the extent of conjugation, but not much more. And so that's why I tend not to use UV spectroscopy in this course, especially since we have access to infrared and NMR. Oh, NMR. Like, why do you need anything else other than NMR? Chuck it all. Go NMR. NMR mass spec. But what's on your bench? On your bench, in your lab right now, there is probably a UV spectrometer and an IR spectrometer. The NMR is in another room behind lock and key, maybe even defended by men in white coats. The mass specs, well, actually, you could have a benchtop mass spec. That's quite common these days too. But NMR is a very big, very expensive instrument, and even though it's very powerful, it's not necessarily the most available. What's available right now in your lab to see if that reaction worked right at this moment? UV-vis and IR spectroscopy. Quick check. Did your transition happen? Did the conjugate? You were doing a hydrogenation. The conjugation should have changed. You're doing a hydrogenation. The functional group should have changed. So these spectroscopic methods are useful. We tend not to put a lot of emphasis on them for structural elucidation, but you'll find them very useful for following the progress of a reaction. If you know the absorptivity of the molecule that you're interested in here, you will, of course, be able to calculate its concentration using UV-vis spectroscopy. Very useful for that. Very useful for following reactions and doing kinetics. So I'm not going to diss it. I'm just saying not too useful for structure. But of course, it does have its day. So read the chapter on UV-vis spectroscopy. It is part of this course, even though I'm not giving it a lot of respect. It is still an important part of spectroscopy, and it does have its uses. There'll be another presentation on the instruments of UV visible spectroscopy. So we hope you enjoy that, and keep up with your reading.